left-hand side figure. That's what happens. The AVA is the one you just learned, the active virtual control. And that is not sensitive. So AVA is not sensitive to the system parameters. Okay. System parameters. Again, that's only instability. All right. The AVA is not sensitive to the system parameters. That means if you don't model your system very well, for example, your mass, you miscalculate your mass, you miscalculate your stiffness, then even that, because AVA is a dissipative control design that is not sensitive to the system parameters, the system is still stable. Even though that is, the system is still stable. However, the performance may not be satisfied. In other words, AVA just guarantee you the stability, does not guarantee you but does not maybe it may not. It's better, may not. But may not meet your performance. So may not meet the performance. All right. The LQG. So, but here, however, LQG is better in some sense that because LQG is designed to meet your performance. But LQG designed to meet your performance if your parameters are not exact, then it may not be good because it may not be stable. So, because of that, we add them together. If we add LQG and AVA together, that's these figures. So you add LQG plus AVA together, then your right-hand figure, that's the green color. That means you are stable and also meet your performance. Here we have a 7.4 second to meet your performance. Here we have 3.8 seconds to meet your performance. In other words, if I add LQG on the top of AVA, then I can make my performance much faster. So this is 7.4 seconds to meet your performance. This is 3.8 seconds to meet your performance. That's what this is real sense. This is not simulation. This is real experiments. This HAC. What do we mean HAC? H means high, A means authority, C means control. Okay. Now we have LQG. Here we have LQG. This is high authority control. All right, and the AVA is a low authority control. The high authority control doesn't mean it's always good. Low authority control doesn't mean they're always no good. All right. This really for stability. This is for performance. So the controller design for performance we call high authority control. The controller for stability we call low authority control. So if we add them together, then that become the better design for only a design alone. So this is this experiment is all those you see it here, the red color, blue color, and green color, they're all the real data in the lab, in the NASA lab. So this is the curve. You can see that there's a design, there's a core index, numeric index equal to the energy times LOS, line of sight. LOS means line of sight. This LOS is line of sight. Line of sight is a line of sight, the arrow. So you look at this, the LQZ, HAC, and LAC, AVA, and this LQZ is good. Line of sight is index is good, but it becomes unstable after 20 seconds, and that is no good. Right? AVA, in terms of merit index, is not as good as LQZ. However, after 20 seconds, it's still stable. So when time keep going on to 100 seconds, the LQZ will going up, the merit index going up, and the AVA going down. Right? Now, if you add them together, then they are in the middle. Now the green color, that is the merit. The merit is good. Really, after 20 seconds, it's really good. But before 20 seconds, it's better than LQZ. It's worse than LQZ, but better than AVA. And that is the message I try to tell you, that sometimes one control design may not meet the performance. So you probably need to have like a two control design, add them together, and that gives you better performance. This is the very practical the exercise. So like 101, type A 101, perhaps if we add one more control, we add HAC, high authority control, then it will be even better if we can do that. But of course, it may not be necessary because the earthquake don't come every day or every second. All right, this is we call high authority control, low authority control, and this is to give you a better idea. High authority control only, it becomes unstable. After about 20 seconds, it's growing. The response is the line of sight is white. This line of sight is growing, then that becomes unstable. And U is also growing. It's growing. This is the control is the control turn on after about 10 seconds. Control turn on after about 10 seconds. And then if you have also high authority and low authority control, the same thing. The controller turn after 10 seconds, and it's still stable. So that is good. In this system, we have a consistent, we call persistent input. A persistent input, like the earthquake coming, keep going until earthquake gone. When earthquake is still there, we have a persistent, disturbances. Persistent disturbances, and this really have a persistent disturbances. Okay. All right. Now we conclude this controller design. This AVA controllers we introduce in this class and it is showing that the robustness and effectiveness to dissipate the vibrational energies. And in your homework, we will give you some of the exercise about frequency matched AVA. For example, in the homework number 4, I say, okay, the AVA frequencies and my system frequencies are identical. Okay, let me just show you this. When you design a controller, you need to be very careful about those. If we have a system, this is system. This is K. And when we design a controller, I call this is MC. This is KC, and let us see. Okay. The frequencies of this, if without this, the frequencies of this is KOM square root. That's my frequencies, right? My KC, this KC, if we design this system like that, you rather to design a KC such that its frequencies probably identify K of M. Right? You know why? If we have a vibration energy for this system, if this is the design, I want to dissipate the energy, the system energy, then those two systems has to be oscillating. 它们必须共振. They have to be oscillating. If they are not oscillating, then the energy, this one won't flow to here. The energy, this energy. We have to have energy flow to this here. And when energy flow to here, then this system will be able to take out the energy. That's just practical problems. If a system like to take out energy from the other system, I have to make sure my system oscillate with the other system so that the energy will be able to flow to my system, and my system then will be able to take the energy out. Understand? No?